So in the previous video, we talked about the Carnot cycle and heat flow and work done. So naturally, if I have, I'm going to draw this again. Once again, I don't really care about the numbers here because I don't want to calculate them because that's a lot of work. If I have a Carnot cycle, you have an isotherm, you have an adiabatic curve, you have another adiabatic curve, and you connect the two of them with an isotherm. So you have a cycle that looks like this. And I know that this is all one temperature, this is all one temperature difference. So this line, or this curve, is an isothermal curve where everything on that line is the same temperature. So this is temperature hot and temperature cold. So when we ran it before, in the last problem, in the last lecture video, we had it going this way. And so we had work coming out here and heat flowing in from the hot reservoir. Because one of the things that you've probably experienced in your life is that heat generally tends to flow from hot things to cold things. Right? Like heat from high temperature to low temperature. So it wants to then, I guess let me go back to my red so we can differentiate these. And so it wants to go like this. So it wants to go like that. And work you have to put in, and it goes like this. Now, for a refrigerator, is what we said we're talking about today, we want heat to flow in from your cold reservoir because my refrigerator is colder than the outside of my house, or the rest of my house, right? And so I want to be taking heat out of your refrigerator and it pumps it into your house. And so that's going to take work. Let me pause this and write this down so you don't have to watch. So that's not what engines normally do. It usually runs off of a heat difference. So I can normally an engine. Let's write this down. You get some hot reservoir. Something that gives you, something that's warmer, right? And you have energy flowing from this hot reservoir into your engine. And then you get heat flowing out. Less heat. I guess I should make this thinner, really, into your cold reservoir. And the difference in energy is the work you get out. Now, a refrigerator we want to run the other way, or an air conditioner. So I actually want heat to go from cold to hot. So let's redraw this. I'll pause it while I redraw it so you don't have to watch. For a refrigerator, I want the heat to flow from the cold to the hot. which means I have to put in work to my engine. So I'm not getting work out. That's why refrigerators take energy. Like a heat engine like this, it can run off a heat difference. I'll have to post a video maybe of a Stirling engine. I think I have one in the classroom, but we're not there to look at it. And that's, you can take this Stirling engine and put it on a cup of tea. That's how you spell Stirling engine. That's what I like to do, because you guys know my thing for tea. You can take your Stirling engine, put it on a cup of tea, and then the heat difference between the air like underneath the engine where it's hot and the rest of the room where it's cold is enough to make a wheel spin. And so yeah, that's just a really cool visualization. Okay, so what does this look like in terms of how do we make this happen? So let's say we have some gas cycles that look like these. So some isotherms and adiabats. This is a Carnot cycle. Then this is an isobaric process, and isochoric process. And you're making a square. And here we can have another isobaric connected by adiabats. Or you can even do isotherms if you wanted. So the real trick is I want this to, I want to have my heat flowing out into my hot reservoir. So we are requiring that we want heat to do this. Heat, right? Wow, heat. Yeah. So which means that, because I know that for an isotherm, it's probably the easiest one to do this on. For an isotherm, I know that the change in internal energy is 0, right? Which means that my work must be going this way. So I've just switched the directions of this. So what if I actually just switch the direction of the cycle to figure out how to make this work? What if, instead of having it flow clockwise, what if I had it flow counterclockwise? And so that is the thing you can do. That would make this a refrigerator. So what about on this example? Well, let's try that idea and have it flow. Oop, wrong way. Have it flow this way. So if I have it flowing this way, I know that work is not leaving the gas but entering the gas, because we are compressing it. And so I don't know which way heat flows. I'd have to do a little bit of math on that. Actually, I do know which way heat flows, never mind. Because it's just going to be the opposite, because we've switched the direction. We're just undoing the process. So I know that my heat is going to be going this way. And then my heat also must be going this way. And the work must be going like that. And then on these sides here, got off where I couldn't see a little bit. On these sides over here, since we are cooling this process down, we're going from a high temperature to a low temperature, and we are also doing it without changing volume. It means, once again, my pressure is decreasing because things are slowing down. That must mean I have heat flowing out. And the opposite's true in this one, so heat flows in. And there's no work done on those cycles. So, and we can continue this for this guy too. Same idea up here, and these are adiabats, so no heat exchange. So I could just do the same processes down here. So let's just go ahead and write this down. So if you want to go, if your gas cycle is clockwise, that means you have a heat engine that does work. You get work out of it. If you have it counterclockwise, it means you have a refrigerator or an air conditioner. And that requires a lot of work. All right, I'm going to call this one here. I'll see you in the next video, guys. Have a good day and stay safe out there.